Kieran is the engineering and interface manager for EirGrid on on the Celtic Interconnector project. Kieran holds a BEng in electrical and electronics engineering from UCC and is a chartered engineer with the IET. And I'm looking forward to hearing all about this project as it comes near to where I'm from. And I've been watching it being built over the last while. So thank you very much, Kieran, and off you go.
Fantastic. Thank you for that. Yeah, so it's great to be invited to come and give an update on this project. It's about 2 years, I think, since I last gave an update to Engineers Ireland on the project. That was to the Cork region. So a lot of work has happened, a lot of on the ground works have taken place, and we still have a road ahead of us, let's say. But yeah, a lot of good insights really that I hope to share with you today. So I guess to begin, just a brief overview of what is the Celtic Interconnector. Essentially, it's a joint development being promoted by EirGrid as the TSO in Ireland and Ortia in France, the equivalent. And the two entities have created a joint venture called CDAC to deliver this interconnector and all of the infrastructure associated with it. So CDAC is the Celtic Interconnector Designated Activity Company. The I suppose the end result here is that we'll have an electrical link that will be capable of transferring 700 megawatts between the power system in Ireland and the power system in France. The 700 megawatts is not an arbitrary number for this link. It was the output of a number of quite detailed network studies. Obviously, Ireland is a much smaller system than France, and you may have seen recently we have exceeded 6 gigawatts, which is a new record in terms of demand on the island of Ireland. So 700 megawatts will go a long way towards meeting our security requirements in the future, our energy security requirements. But 700 megawatts will be the largest infeed or outflow from the Irish system. So to date, that has been our existing interconnector, the East-West interconnector between Dublin and Wales, well, Meath and Wales, I should say. So yeah, 700 megawatts. It is maybe on the lower end of transfer capacity for interconnectors of this scale. However, it's tailored to suit the needs of this project. Overall, it'll be 575 kilometers total length, and the largest proportion of that is in the subsea environment through the Celtic Sea, 500 kilometers in the sea. It's a project of common interest since 2013, so that's a very useful status for the project to have in terms of its ability to move through the planning and consenting processes, etc. It has been part funded through the Connecting Europe Fund at an EU level, and we were successful at a grant award back in 2019 for 530 million. So a large proportion of the cost of the interconnector is being funded through the EU. It's required consenting and planning I suppose, adherence and submissions across 3 different jurisdictions. So we had here in Ireland for the onshore. We had UK consenting requirements as we passed through the UK exclusive economic zone, not through their territorial waters, and then similarly on the French side. The engineering, procurement and construction contracts were then awarded in November 2022. And yeah, we're here 2 years down the road with construction well underway. Just very briefly, it's remiss of me not to say who EirGrid and RTE are. So EirGrid is the state-owned operator for Ireland's electricity transmission grid. Essentially, we're responsible for ensuring that there's always sufficient energy to meet the demand on the island. We operate the wholesale electricity market, and we explore electricity interconnectors with our neighbouring countries, and hence why we're here doing this with France. EirGrid also has a new role as the offshore transmission system operator and asset owner. And again, having this interconnection will really work hand in hand or side by side with our offshore role here in terms of expanding the renewable generation and the use of it here in Ireland. Ortea then are equivalent, obviously much larger player in the European context, are very well interconnected with their European partners and with Great Britain as well. So a number of interconnectors. And at the same time that they're developing Celtic with us here in Ireland, they are developing the Biscay Gulf project with Spain as well. So yeah, much more integrated system than we have here in Ireland, which is often referred to as being on the edge of Europe, this little island on the edge of Europe with no energy connection to mainland Europe. In terms of the benefits that the Celtic Interconnector will bring, it will improve market integration, so it will allow the single electricity market here in Ireland to connect with the EU internal energy market. There are price differentials in play at the moment, and having an interconnector will have a balancing effect there in terms of the price. It will allow the increase of renewable energy sources for electricity, potentially reduce curtailment requirements, allow increase of renewable generation, and becomes a key enabler of Irish government policy. And the third major benefit really is enhancing our security of supply. As I mentioned, we're an isolated island with low levels of interconnection to other electricity markets. And to allow us to have that integration to move to a less carbon intensive generation source, we can use these interconnectors to facilitate that increased use of the renewable energy while maintaining our security standards of supply to the island. In terms of how we've progressed the project to date, I myself have been on this project in various forms over the years, but permanently on the project since late 2018. It was first mentioned in the business planning back in 2011, and essentially there was a preliminary feasibility phase undertaken where we looked at was there mutual benefits, what technology, or even if the technology existed to complete this interconnector, and probably most importantly, what would be the cost of delivering this infrastructure. It's no small project, and obviously comes with high costs that must deliver on the benefits. At the end of that period, stage gate reviews took place, and the green light was given to move into a more expanded feasibility stage between 2014 and 2016. And it was during this period that physical marine surveys took place to try and identify a marine route between potential landfall points in Ireland and in France. Initial discussions around the project parameters, power transfer capacity, etc., and the continuation of the economic and financial analysis. Again, a review of the project, always in conjunction with the regulators' requirements, etc., both on the Irish and the French side. We moved the project through into what we call the IDPC phase in 2016. So here we entered into a bit more of a detailed initial design. I know that's a bit of a contradiction, but yeah, it's an initial design, but obviously not detailed design. And we started the pre-consultation with the communities in the proposed areas where the infrastructure would be located. In this period also, we submitted an investment request to the regulators in Ireland and France, and essentially then it was accepted, and a cross-border cost allocation was provided by the regulators for the project. And in that period also, we submitted and were successful with the grant application to the Connecting Europe Fund. So 530 million, quite a large investment, which underscores and underlines the need and the benefits of the project. 2019 to 2022 then was more detailed discussions and consultation with the local communities as we refined and ultimately defined where the infrastructure would go in the Cork region. We started the procurement process and submitted our planning applications. And at the end of 2022, we awarded contracts. We achieved all of our consenting. We had our final investment decision and ultimately progressed then into the construction phase, which is where we are now. So equipment is being manufactured. There's a lot of civil works ongoing on the ground, both in Ireland and France, and we're gearing up for our marine campaigns now this year and next year. To give an overview of what we're talking about and where the infrastructure will sit, if I move from west to east or left to right on this diagram, so we have our Knockgraha substation, which is our grid connection point to the existing transmission system here in Ireland. The first piece of infrastructure that we will build is a new 400 kV AC substation. It's going to be a single base station located directly adjacent to the Knockgraha substation. And from there, we will install 11 kilometers of 400 kV AC cable down to the Ballyadam converter site in Carrigtwohill in Cork. From the converter site, then we have 32 kilometers of DC land cable stretching eastwards from Carrigtwohill, a few off-road sections, but mainly along the N25 there towards our landfall point at Claycastle Beach in Youghal. There's a transition joint bay there where the land cable is joined with the marine cable, and off we go for 500 kilometers through the Celtic Sea, skirting to the west of the Isles of Scilly, going through the UK exclusive economic zone, but not, as I say, through their territorial waters. And we come ashore then in the northwest corner of France, in Brittany, a place called Clédaire in Carrier-de-Bec. And from that transition joint bay, there's 40 kilometers of DC land cable to the converter station, which is going to be called Reseau, and that's located directly adjacent to the existing grid substation in La Martyre, which is a 400 kV substation. So that's, I guess, pictorially what it looks like. I'll come back to those individual components in a little while, but I mentioned that we'd awarded contracts in 2022. So that was the end result of a long procurement process, a lot of detailed technical discussions with the market. And ultimately, we signed contracts with Siemens Energy to provide the infrastructure for the Ballyadam converter station in Ireland, the Gogginstown AC substation in Ireland, and the Reseau converter station in France. That was one EPC contract. The other then was issued to Nexans for the provision and installation of the HVDC submarine cable, about 500 kilometers in the marine, the HVDC land cable in France, the HVDC land cable in Ireland, the HVAC land cable in Ireland, and then the fiber optic cables that will be installed alongside of all of these power cables. So we have two EPC contracts. Then on the Irish side, we also have enduring long-term service agreement and inspection, maintenance, and repair contracts signed with both entities as well for the operational phase. In terms geographically then of what we're looking at, this is just a screenshot that I've taken from our website, our interactive website, just to show you the route stretching from Knockgraha there in the west to Youghal in the east. And if I just overlay where the individual components are, so the AC cable route stretches from Knockgraha down towards Carricktool, mainly on local and regional roads there, and we cross under the Cork Middleton Railway, just at the point where the converter station is in Ballyadam. And then eastwards from the converter station is our DC route, which goes again under the same railway, and then to the north of Middleton before it comes down and rejoins onto the N25 for a period. We come off-road at the town of Castlemartyr and rejoin to the east of Castlemartyr back onto the N25, come off the N25 again at the town of Killa for a period and rejoin along the N25 for the most part then out towards the beach in Claycastle. As you can appreciate, there's a lot of stakeholders involved here, and the team has worked very closely with a number of the stakeholders like Gas Networks Ireland, Irish Rail, Cork County Council, TII, and there's been quite good discussions, good relationships built with all the stakeholders down there, and particularly with the achievement of road opening licenses as well. It's well recognised by EirGrid that we can't do this without the cooperation and the interaction with our stakeholders. In terms of the status then, where we are at, so the AC cable route, 11 kilometers, consisting of 15 cable sections, 14 joint bays in quite tight road networks, rural road networks, local road networks. We have the HDD under the live railway as well in that AC cable route. And at this point in time, we're 96% complete with that. So all of the cable has been trenched and ducted. The cable has been pulled through into the joint bays. It's progressing through and there's a few joints remaining. I guess the large component of what's left there is to do that horizontal directional drill under the live railway, which is planned in the coming months. We're going through the last stages of licenses and authorizations with Irish Rail there. For the DC cable route, again, 32 kilometers in length, broken into 23 cable sections, 22 joint bays. As I said, there's a number of off-road sections, but we're progressing quite well. 65% of the trenching and ducting is completed, and that DC cable is under manufacture at the moment in Charleroi in Belgium, and we should see the first deliveries of that cable coming to site in the next couple of months. The Ballyadam converter station, we concluded a significant earthworks stage in May of last year, and I'll spend a bit of time focusing on that later on in the presentation. But it's allowed us to have our foundations and our platforms constructed now, and our steel structure is fully erected, and we're moving now into the phase of commencing the building services and electrical installation, with a view then to starting commissioning at the latter end of this year and into next year. Gogginstown 400 kV substation again is progressing quite well. Main civils are nearing completion, and then similarly to Ballyadam, we'll have building services and electrical installation commencing imminently, with a view then to having commissioning commencing at the end of this year and into early next year. Maybe just to touch point that before I start going into some of the more detailed terminology, just a quick slide on electricity interconnectors and I suppose what they are. They can be made up of AC and or DC components, and they're ways for different electricity grids, let's say, to exchange power between themselves. It's more common, mainly maybe for people to think of interconnectors as being HVDC. Obviously, ours is AC plus DC. It's going from the Knockraha substation to the La Martyre substation in France. But the largest component of it is the HVDC element, and that's a point-to-point transfer of power. And essentially what we do is we take the AC power from the grid and we convert it to DC at a rectifier converter station. We then transmit in DC power to the opposite end of the link, to the inverter converter station, where the electricity or the power is converted back from DC to AC and can be transmitted then onto the grid at the other end. Now, power can flow in both directions, depending on the market conditions. So there might be periods of the day when the power will flow from Ireland to France, and then depending on the market conditions, we will change the direction of that power and import from France. And that will be done under controlled rates, ramp rates, for example. But the benefit of the technology that we're going to install here is that we can have relatively easy flow of power from Ireland to France or from France to Ireland. And the converter stations in Ballyadam and Reseau can be inverters or rectifiers, as I say, depending on which way the power is required to flow. So I felt it was important to put in that slide before I put this one up when I started talking about, what a converter station is and the various elements of it. But essentially, this is the design for the Ballyadam converter station in Carrigtwohill. It's very similar to the Reseau converter station site. There are differences in the site conditions and layouts, let's say, that would be unique to the locations where they're to be built, but essentially they perform the same function. So we have our DC cables coming in from France. They come into the DC hall of the building there on the right, and they get then the power then transfers into the converter building, and this is where the switching process or the transformation process takes place from AC to DC or vice versa. It's done through IGBTs, a lot of electronic switching, let's say, with a very sophisticated control system. And the output then is AC electricity, which comes then into let's say, the middle of the site where we have our transformers. So there's 4 transformers there. So we have 3 single phase operational transformers and then 1 single phase spare, should there ever be a faulted phase unit in the future. And then over to the left, we have our AC yard. So essentially this is the bay that allows the connection of the AC cable for the transmission of the power from the converter station to the existing transmission station up at Knockraha via the Gogginstown station. You might see here we have some large items in the bottom left-hand corner. They're AC air core shunt reactors. They are unique to Ballyadam, let's say. They're not at the Reseau end of the link. They're there to essentially manage the voltage step change that occurs when we switch in the 11 kilometers of AC cable linking this site to the Gogginstown and Knockraha substations. I mentioned the heat that's generated from the switching process. So there's a cooling system installed on the site, and we have outdoor coolers there. And then there's a storage building installed to store our strategic spares, spare cable drums, etc. So that was the design, and this is a picture taken from site this morning to show the physical progress. So as I say, the steel structure is fully erected now and is undergoing its first layer of cladding. That's not the final cladding, it's just the first skin, let's say. We have our attenuation pond in the northeast corner there, control building is with the red indicated lines on top of it there, just from a working practice at the moment. And then in the center of the site, we have our plinths laid for our transformers, and the erection of the blast walls between those transformers is ongoing at the moment. And then to the left, we have all of our plinths for the AC equipment installed. You can see the more robust plinths there on the southwest side for those AC air core shunt reactors, with the steelwork for the building under erection as well at the moment. So we're progressing quite well. We will see a lot more progress in the coming months, and we'll start to see a lot more of the electrical equipment being installed on the site itself. In terms of the Gogginstown 400 kV AC substation, so it's a single base station located directly adjacent to the existing transmission substation. There is an element of work between EirGrid and ESB networks as well for the installation of transformers within the fence of the existing Knockraha substation. That's outside of the scope of the EPC contract for Siemens Energy, but the two projects need to work in parallel, and there are many teams here in EirGrid working on that at the moment, and ESB. So again, that's the design, and here we are in terms of the physical progress. We can see the control building fully erected, the equipment plinths installed. You may not see it there, but the AC cables have been run up the termination structures there, ready for the actual terminations themselves to be made. So again, a lot of significant works ongoing on both of those sites at the moment. To give just a brief overview of the electrical cables that are going to be installed. So we have AC and DC cables here. So if I just start with the DC cables, they are 2500 square mil aluminium XLPE cables, so cross-linked polyethylene. And the DC voltage level, we're at plus minus 320 kV, so positive 320, negative 320. And the submarine cable, as I say, 497 kilometers. It's a similar cable then for the land portion in Ireland and France, 2500 square mil aluminium cable. It's, I suppose, not as mechanically protected as it would need to be for the marine cable. So a lot of the armoring wires, etc., are not required for the land cable, but very similar in terms of its makeup. The image on the bottom left actually is the submarine cable. So you can see that we have profiled aluminium wires, not round wires, in 5 concentric layers around a core. We have our inner semiconducting layer, the insulation medium of the XLP, the outer semiconducting layer, and the various lead sheets, PE sheets, bedding tapes, armoring wires, etc. For the AC cables, they're similarly 2500 square mil aluminium XLP 400 kV cables for the 11 kilometer route between Knockraha and Ballyadam. And again, a picture paints, I suppose, a thousand words. There's a couple of pictures coming up now, just how the cables, at the end of their extensive design period and the review by CDAC, the teams in EirGrid and Ortia, the AC cables went into manufacturing, and delivery of those cables to site started. It must have been May, June last year, if not earlier. So about somewhere in the region of 44, 45 cable drums, with each having about 700-800 meters, depending on the position of the joint bays along the route, were delivered to site. And again, just a few images of those cable drums being unloaded in the compound down in Ballyadam before onward delivery out to the various route sections. Okay, and just an image here. This is an image of the AC trench that was being installed just on the road outside of the existing Knockraha substation. So the 400 kV ducts, the 400 kV cable is installed in a ducted system. It's in a trefoil configuration, so think of a triangular configuration with 2 at the bottom and 1 on top, with 2 telecom ducts also installed for the fiber optics in the same trench. So quite, I suppose, narrow enough slit trench. Maybe I wouldn't call it quite a slit trench, but a narrow enough trench. But you can see the scale of the roads in which we're dealing with here. Narrow roads often required road closures to undertake the works and the activities. This is an image then of a joint bay and the cable being pulled into the joint bay. So you see how the cable is delivered to the work site, and is then pulled through in a tensile controlled environment through the joint bay. So at this end, we've got the drum on the back of the truck on a roller system. And at the other end, at the other joint bay, we would have a pulley and a winch. Again, careful coordination to manage the tensile stresses on the cable as it's being pulled through the ducted system. The next couple of images, yeah, again, just show that cable being pulled through, the completion of that cable pulled through from the other end of the joint bay. And here is an image then of the cables actually with the jointing completed and in preparation for the backfilling of that joint bay. The way we have set it out here in Ireland is that where we have a joint bay, and given the nature of the roads that we're dealing with, we needed to keep roads open insofar as possible while the jointing was occurring. So the blue container on the left is the jointing container, and that's the joint bay location. And what we've done is opened up passing bays to the side of the joint bay that allow the controlled movement of traffic while the jointing is continuing. And then when the jointing is completed, the road is reinstated and the passing bay is put back to its original form. Obviously, it takes a little bit of time, but the intention is that it will regain its original form prior to any of the works having been completed. It's worked quite well from what I hear from the teams on the ground down there. Moving on then from the, well, before I go to the Irish landfall, I suppose a similar process is being followed on the DC. There's only, I suppose, 2 power cables as opposed to the 3 on the AC route. It's a slightly narrower trench, and we're moving along the N25, so slightly larger roads as well. So that is progressing quite well for the DC route, but following a very similar process, and the jointing will follow an identical process, let's say. Upon returning after Christmas this year, we've opened up the work site at the landfall point in Claycastle Beach in Youghal. So we've established the compound, and preliminary works have started there now in advance of the marine works this year. What you can see is the commencement of sheet piling on the beach, which will allow the installation of a cofferdam and ducts to be installed, then ready for the cable to be delivered in the appropriate campaign, be it this year or next year. So we're looking at 4 campaigns between 2025 and 2026 to install the 500 kilometers route. Let's say it's 1,000 kilometers of cable when you have 2 cables in the bundle, but yeah, the route of 500 kilometers. So this is again just good progress. It's another indication of how well the works are proceeding, and the various activities required at the landfill. If I can just go back maybe and spend a little bit of time focusing in on some of the main challenges that we've faced since we started the construction phase, and the one that I'd like to maybe spend a little bit of time on is the ground risk and the foundation design for the Ballyadam converter station site. It has posed a number of challenges to us, both in identifying the site and confirming it as the location for the converter station, but then in terms of ensuring that there's a design that is installed that is fit for purpose and for the lifetime of the interconnector and the asset. So we would have developed, we would have followed a 6-step process, let's say, here in EirGrid for the development of the interconnector, and it ranges from step 1, how do we identify what we need to do to reinforce the electricity grid? To let's focus in on step 4, where exactly should we build? How do we identify the locations of the converter station, the substation, the AC cable route, the DC route, the landfall point exactly, and then into the planning process. So really in step 4, we were looking at the various locations where we could locate the infrastructure. And there was a lot of multi-criteria analysis done in terms of, how a certain location would perform relative to another. And each location would have been assessed from a deliverability perspective, a technical performance perspective, economic, environmental, socio-economic. and obviously it needed to work with the AC and the DC routes for the cable routes, etc. And ultimately, the output of all of this process, and it was done in a very sequential, phased process, where we analyzed performance matrices, we did multi-criteria analysis, but the location of Ballyadam came out as initially the emerging preferred best performing option before it became the preferred option and was included then in the consenting application for the infrastructure. But in choosing Ballyadam, we carried with us known risks for the ground condition on the site. And essentially, the geotechnical issue that we had on the site was karst features, and there's many of those present on or in the vicinity of the site. And it certainly brought me back to my Leaving Cert geography when I started seeing terms as dolines, turlocks, etc. But I've become quite familiar with these over the course of the last number of years. But Ballyadam has this risk. It was subject to a lot of analysis, and it lies somewhere between an engineering class K2 to a K4 in terms of useful to complex karst. So we entered into the process knowing that this would have to be dealt with, and we structured and analyzed arranged ourselves and the EPC contractor to be able to deal with it. Just to give some of the examples, again, a number of reports were produced in advance of us determining Ballyadam as the site for where we would like to build the infrastructure. But we see some of the karst features here, active collapses in various elements of the site, sinkholes opening up, Sophosion dolines, etc. So we knew what was there. The site had been subject to a number of surveys by previous developers. It was a brownfield site. It's an IDA site. They're just to the west of Middleton. So as I say, we knew what we were getting into, and yeah, there was a varying nature across the site, and it just required us to undertake detailed analysis of what the appropriate solution would be. Now, we didn't necessarily mandate or dictate what that solution would be. We let it up to our EPC partners, contractors, to come up with the solution, for which we then analysed and challenged, etc. To describe the site, it's got an overburden layer of glacial till sitting on top of a limestone bedrock, and as I say, it varies across the site. It's not a uniform or consistent position, let's say, across the site. So we would have taken a geophysical survey in 2021, and then Siemens Energy, as the contractor, would have taken another survey in 2023, with the objective to really understand the ground conditions. What soil is there, what rock stiffness is there. We wanted to profile the rock head, essentially identify the weak spots or any other anomalies across the site. And there was a number of techniques used, with borehole pits, percussion boreholes, rotary boreholes, dynamic probing, all of that in conjunction with groundwater analysis. We were acutely aware that there's an aquifer being fed by the surrounding area, and as groundwater rises and falls, it can have a washing effect, let's say, in terms of when it rises, the water level comes up, and as it dips, it can wash material out from the karst features. So the solution that was arrived at was initially to strip the site back. A large excavation was undertaken, I think down to about 13 meters AOD, from about 16 point something meters, if I recall correctly. The existing karst features were stripped back and exposed, and they were then treated. They were backfilled with granular material and compacted down. And then we undertook what was known as rapid impact compaction across the entire site. So again, we wanted to compact the entire site, to densify the soil, and to make its behavior homogeneous across the site. And to a layman like myself, not a civil engineer, we essentially pounded the ground with a 9-ton hammer. The image on the bottom there is just a picture from partway through the process, but you can see the various discs of the circular hammer, let's call it. And the objective again was to achieve an effectiveness of a depth of up to 4 meters. And there was criteria there in terms of, when we could stop the pounding, let's say, when we saw a maximum of 15 millimeters of average settlement over the last 3 blows of the hammer. So that was the first step. Then we installed a high tensile strength geogrid across the entire site. So we wanted, again, to protect against the scenario of reactification of karst in the future. If a new karst feature was to occur, we didn't want sinkholes, etc., to start opening up. So we looked at this tensile strength geogrid, and the design parameter of that was a 2-meter void spanning capacity, so that we are protected and guarded against karst features, I suppose, with that 2-meter void opening up again in the future. Again, that figure wasn't arrived at by accident, subject of a lot of detailed analysis and engineering. We then installed a bentonite sealing membrane to stop the vertical infiltration of rainwater, so rainwater coming from the top down. And as all this was going on, we were continuing our analysis on the effectiveness of the works, and it was identified that under the heaviest load point of the site, which would be the transformer area, there were soft spots identified at depth. So the solution there was the installation of controlled modulus columns, or CMCs. And essentially what we're doing is drilling down, we're using a continually flighted auger under pressure. And then once we achieved the required depth, the auger was extracted under pressure, and a cementitious material was pumped in. Not to be considered as a pile, as it doesn't touch the bedrock. But I suppose, again, if I go back to my layman's terms here, it was described to me, and I've always kind of latched onto this. If you take a sponge and you start adding cocktail sticks to it, over time that sponge gains rigidity. And essentially that's what we're doing here. We're giving the soil and the ground conditions stability in the area of the highest load of the site. Ultimately, following the completion of all of those steps, we were able to start pouring our platforms. You can see the main platform there on the left for the building, and in the middle is the form work and the rebar work going in for the transformers post the CMCs. To just continue on, I'm keeping one close eye on the time here, because I do want to leave a little bit of time for questions at the end. But just to describe, we spent a lot of time here talking about the Irish side. The equivalent works are happening on the French side. So they're progressing through the DC cable route at the moment. They have completed their horizontal directional drill at the landfall. And the converter station in Reseau is a little more advanced than it is on our side in Ballyadam. But then it's not really a competition, I guess, but they didn't have the complexity of the earthworks that we had to deal with in Ballyadam, as I've just described. So this is a picture of the status of the converter station in Reseau. As you can see, the building is fully cladded with its final rendering. We have the blast walls for the transformers installed there in the middle, with the heavy duty access road under construction. The spares building has been installed, and the AC plinths there on the left are under development as well. So quite advanced. We are closing the gap on them though. It's not a competition. In terms of the landfall then in France, this was undertaken last year. It's a very different geography, I suppose, and landscape to what we're dealing with in Ireland. There's a lot of hard granite at the landfall point, so they had to do a horizontal directional drill for about 600 meters out from the landfall point. So this is just a few images of the rig being set up on the coastline there, and you can just see some of the rock that had to be drilled through out about 600 meters into the coast there. While that drilling was occurring, about a couple of kilometers, maybe 3 kilometers down the coast, the ducts were being assembled to be pulled through the various bores that had been dug by the horizontal directional drill. They were then floated out and delivered to the location and pulled through the bores successfully up onto the landfall point there in the background, as you can see it. So that was a big project risk that was successfully undertaken and completed last year. On the French DC installation, here's just some of the images. Apologies for the quality. I took these from a report there over the weekend, but you can see differences, I suppose, in terms of the approach based on national and regulatory requirements in France, but essentially it's the same. 2 power cable ducts with 2 fiber optic ducts installed alongside it. The French side also had an additional challenge in that they had to cross under a river and at the same time under the high-speed rail, the SNCF railway. And instead of a horizontal directional drill, they undertook this with a micro-tunneling machine. So 2 shafts were dug either side of the rail and the river. Can't recall the precise depth, but probably 10 to 20 meters deep there, I would imagine. And the boring machine was lowered in there on the left, and the image on the right is it being extracted from the corresponding shaft on the other side. So again, another big project risk that was successfully undertaken last year. So in terms of the onshore work, I hope I've given a good overview of where things are at. Things are progressing well. No real blockers, I suppose, ahead of us, aside from hopefully Touchwood getting under the Irish Rail line there at Ballyadam in the coming months. In the offshore then, where we have a high focus on that for this year and into next year. So the offshore cable is under manufacture at the moment in Halden in Norway. The image on the screen is the Nexans flagship vessel, the Aurora. It's got a 10,000 ton turntable on that to carry the cables. So, we can achieve campaigns of up to 125 kilometers at a time using a vessel like this. So not insignificant in scale or technology. The marine route, just a quick overview, 497 kilometers outside of the UK territorial waters. We're avoiding special protection areas. We do have a variable seabed geology. We go from having hard granite on the coast of France to areas of clay, silt, and harder and softer materials throughout, as you can imagine, with some complexities with mobile sand waves, etc., to deal with. But ultimately, nothing that can't be overcome. There's no major constraints. We have to cross about, I think it's 18 other cables, namely telecom cables. So we have to enter into crossing agreements with the utility owners for those. And all of those are underway at the moment with support of, I suppose, specialist consultancies, etc. Really then where we are at, end of 2024, we have started the manufacturing of the offshore cable coming from Halden in Norway. We're progressing with the installation and jointing of the DC cables in Ireland and France. And as I say, the AC cable in Ireland is largely complete. And you can see the progress that we have with the converter station installation. So the focus then for the next 2 years is heavily on the marine side. So we hope to do 2 campaigns this year and 2 campaigns then into 2026. And then we, in parallel, continue with the commissioning requirements for the converter stations. All going well, successful interconnector system tests at the back end of 2026. And we will then enter into a 3-month trial period, which will allow full takeover of the asset on the 31st of March 2027. So we have, as I say, we have a lot of work done, a lot of engagement, I suppose, with the authorities and the stakeholders in Ireland and France to allow us to make the progress that we're making. And then we're continuing with the marine side, a lot of engagement with fisheries, and at the landfalls, I suppose, in Ireland as well with the relevant authorities there. So really, I think that summarizes where we are at. And I think I have some time remaining. I'll hand back to the moderator for any questions. I can't see what questions have been submitted, but I'm quite happy to take them as they come in.
Excellent. Thank you very much, Kieran. That was really, really interesting. It's great to see the project progressing almost all the ways through. Only another 2 years to get it. So the next 2 years, as you said, 2 years since your last presentation. So the next time you present to Engineers Ireland, you'd be finished and you'd be telling us how great a job it was. It's just something interesting you said, because I'd completely forgotten from my past, was the karst limestone on the site. I spent when I was a graduate filling a hole not too far from there and wondering, was it ever going to fill? They can be very, very big and deep cavities and underground chambers in that area. So that was interesting how you dealt with it or tried to remove the risk. Before I hand you over to Susan, who's going to go through the questions, can I ask one question that I'm kind of interested in? What's the form of contract on this with 2 nationalities or 2 countries? How is that dealt with in this case? Is it some sort of FIDIC contract, or how does it work when the 2 companies are working in 2 jurisdictions?
Yeah, that's a good question, and you're going to open up a lot of wounds for me here. We have procurement law, and then we have contract law, and obviously we have the two different jurisdictions. And while we were deciding and determining how to do this, COVID hit, and yeah, we did a lot of this via teleconferencing with our counterparts in France. So quite difficult, I suppose, to come to agreement on heads of terms, form of contract, all of that. But essentially, we have a FIDIC type contract with Irish and French specific requirements added into it. So I don't know, would you call it a hybrid or a
Yeah.
mongrel? But
And is the
yeah,
one entity is the commissioning authority, or how does that work? Are you both? Did you set up a company to do that, to do
yeah,
the
CDAC.
contract?
So CDAC is the joint venture. So that is the delivery mechanism. The
That's the
contracts have been
client.
played, yeah, between CDAC and Siemens Energy, and between CDAC and Nexans, with the intention then that when the infrastructure is delivered, we've taken over the assets, and at the end of warranty periods, excess, etc., those assets will be divested back to the parent companies, which would be EirGrid in Ireland and Ortia in France, with the various maintenance regimes and processes for undertaking maintenance and outages, etc., developed between us.
Interesting. Okay. Going to hand you over to Susan, who will go through the questions that are up on the screen at the moment. Thanks, Susan.
Great, thanks, Joe. Yeah, questions are coming in fast. I think we had over 420 people attending, a steady number during the call, so that's possibly a record for the civil division, and we were already topping the Engineers Ireland webinars for this year, so great interest in this topic. So I'll go through a few of these here. First one, I suppose, what were the factors in deciding the megawatt size of the interconnector?
Yeah, primarily led by Ireland. I'll be transparent and honest here. We're a small system. As I say, we've just breached the 6 gigawatts in terms of demand. So if we were importing, 700 megawatts, and all of a sudden it were to trip and we were to lose that off the system, it would be a shock to our system. It may not be felt on the European system in a well interconnected grid, but for us it would cause a lot of issues. So when in that scenario, we have to carry enough spinning reserve, primary, secondary, and tertiary reserve, so that the supply to the system, let's say, and to the end users isn't interrupted. So 700 megawatts was the limit that we could account for, let's say, and that was the subject of a number of detailed network studies on the Irish side. Ordinarily, for interconnectors of this scale at 320 kV, you would be looking at a gigawatt or up to 1.2 gigawatts. However, for the sake of the Irish system, we're at 700 megawatts, and we will be the biggest. Now, if we start adding more interconnectors in the future, you might see that limit start to increase as we have that safety net behind us. And you might have seen recently that a Greenlink interconnector has been commissioned between Wexford and Wales. That's a 500 megawatt interconnector, I think. But as the fleet of interconnectors increases, we might see that threshold of 700 megawatts increase as well.
So it's as much a redundancy thing as anything else.
Yes, we don't want to be too greedy. We do need power, but we have to, one of our core remits is ensuring the security of supply for the system.
Great. What would the level of losses be across the interconnector?
Yeah, that's a key consideration, and I suppose the converter station losses, you're looking at less than about 1% or less than 1% for each converter station. And then the cable itself will add in, a couple of percentage points there as well. Now, I don't want to get too specific here. There's some commercial elements, but it's much better than it would have been a few years ago. We have a modular multi-level converter. So we're switching across smaller voltage divisions, let's say. We're not going from the full plus 320 to the minus 320 to create our AC waveform. And that has allowed, I suppose, losses to be lower than what they would have been with the older 2-step or 3-step converters.
Okay, thank you. Some of the questions you may have touched on since the questions came in, but I'll ask some of them anyway. So you said you didn't dictate a geotech solution to the EPC. Would you initially have completed a factual or interpretive geotech site investigation for them to analyse?
Yes, absolutely. Yeah, we would have completed that, as I say, back in 2021, and we would have taken a lot of advice as well throughout the tendering process. Originally, we might have considered that a piled solution would have been the only solution. However, as you get more data, you review some of your survey results, you speak to the people who are tendering for the work, and they are offering other proposals other than piling. We didn't mandate which one it would be. Our primary concern would be that it's fit for purpose and for the enduring life of the interconnector. So I suppose in the beginning we would have looked at a piled solution as the only solution, but it quickly became apparent that it wasn't the only solution and that there were benefits to be considered in proposing a raft type foundation solution as well. But yes, we did have interpretive and factual reports produced and issued out, let's say, as rely upon information as part of the contract, for which then the subsequent surveys by the contractor would have been compared against, and you're into the either refinement and further clarity. Let's say that if you have two surveys saying the same thing, you're in a good place. If you have two surveys each saying slightly different things, you're in a slightly different place. So ultimately, it's been analyzed, checked, double checked, reviewed by external consultants, all of which have agreed that the solution and the processes that have been followed and proposed by our EPC contractor are fit for purpose. And we do have enduring settlement monitoring in place for the site as well.
Okay, that's good. Were there any concerns or discussion on rising sea levels given the location of the landfall site being so close to the coast?
The environmental considerations were absolutely factored in. We originally looked at, I think it was 14 locations or zones, we used to call them, as to where the converter station could be located. And those were 2-kilometer zones within where the converter could be looked at. And they were all compared and assessed against the criteria I analyzed before. So under the environmental, we would have considered those. And a lot of that data, well, all of that data is available on the EirGrid website under I think it's the step 2, step 3, step 4A, 4B reports that were produced. But yeah, all environmental factors would have formed part of our analysis.
Good stuff. Sorry, trying to focus on more of the civil related questions, considering.
I think it's worth asking the security question, Susan. It's come up there a few times.
Yeah, there's a couple. They're coming in like this. 2 seconds. Yeah, I suppose. Are there any considerations given for security regarding, I suppose, the recent anchor attacks that we've been hearing, I suppose, in the North Sea and other areas recently? Yeah.
Well, you can appreciate I don't have a pay grade high enough to be in those meetings, but they are of course of interest to EirGrid, and those discussions will be taking place, but obviously at a quite more senior level. During the construction of the works, the mechanism or the process that is followed is the cable is unloaded, let's say, from the various turntables in Halden in Norway onto the vessel. The cable is then transported to the area of the seabed for where it's going to be laid, and the first step is to just lay it on the seabed, and then another vessel will come in and do the required mechanism, be it jetting or trenching or ploughing of that cable. So the cable will be buried along the route, but there's a period of time between it being laid and where it will be buried. So we will have guard vessels and protection vessels during the construction phase. But I think the questions relate more to the operational phase, the headlines of power cables being cut or damaged, etc. I'd be relatively confident that they are being discussed at the correct levels in EirGrid and government, let's say.
Great, thanks, Kieran. I think you've covered off a good number of questions there, and I think there was one. I suppose if you could maybe just differentiate between the marine installation campaign and I suppose what actually is involved with the marine cable protection campaign. So I think someone was looking to describe what the protection works are.
Yeah. So essentially, we want to bury that cable for its entire length. From landfall to landfall. That is our intention. We've undertaken numerous surveys to understand the seabed conditions and what is the appropriate tool to bury that cable. So I think I mentioned ploughing a few minutes ago. It is what it says in the tin. You plough a furrow and the cable falls in to that furrow behind it. We can do some mechanical trenching for the harder portions of the route. We can do water jetting to create that furrow, let's say, or trench for the cable to fall into. But essentially, that is our cable protection. We will have target depths of lowering, minimum depths of lowering, in terms of how far below the seabed that cable will be. There are areas, though, and we're aware of this, where it's going to become difficult and we may not achieve our required depth for the cables. And then we come into the scenario of additional protection. And that could be in the form of concrete mattressing placed over the cable, or placing of rocks, very harsh term in the industry, but rock dumping, I suppose, over the cable to protect it. So really what we're trying to protect the cable against anchor drags from vessels. We don't want that cable being dug up and damaged. Obviously, any repair in the future here is big money, big impact in terms of time. And from a TSO, a transmission system operator point of view, we want that interconnector humming away nicely all of the time without interruption. So burying the cable and protecting it is a key priority for us.
Great, and maybe we might have time for one or two more. How much time is needed to reverse the direction of the electricity flow across the interconnector?
Okay. Immediate, I suppose, is the correct answer to that. The technology allows us to do it instantaneously. However, to go from 700 megawatts import to 700 megawatts export, 1400 megawatts, again, would shake the Irish system too much. So we have what's known as a ramp rate in Ireland. So we will control the flow. We will reduce or increase in 5 megawatt increments per minute. And as I say, this is all kind of market driven. You know, if the allocation is that at 3 a.m. the interconnector is to be importing 700 megawatts, and at midnight or whatever it's doing X, we need to allow the time for those 5 megawatt increments to occur to achieve that transfer rate at the required market time.
Okay, great. And maybe one more. I suppose, are we learning any lessons from the French, I suppose, in relation to our construction methods, and if they could be applied in Ireland?
Yes, but I would also say they're learning from us. It's you know, we each have our respective expertise. Yes, they have in-house expertise, so they are, I suppose, TSO plus TAO, so they're the asset owners. They have their own maintenance crews. They do operate a fleet of interconnectors delivered by multiple suppliers. So it's fair to say that they have a lot of experience in certain areas, but then we carry a lot of expertise in different areas, and we work well together. We work as one team. You know, I've been working with my counterparts now in France for, I suppose, coming up on 7 years, and I have to say, you know, it's been a very good relationship across the board, not just engineering wise, commercially, contractually. You know, we do learn a lot. I personally am learning a lot. You see today I'm transitioning from an electrical engineer to a civil engineer, for example. But you know, there's so much opportunity on this project to learn, and yeah, we're learning from them. But as I say, we bring a lot to the table as well.
Great, that's good to hear.
Right. I think as it's just gone beyond 2 o'clock, we'll call it at that point. And just like on behalf of Engineers Ireland, the Civil Division, the Electrical Division, and the Energy and Environment Division, thank you very much, Kieran, for another excellent presentation, and wish you and the rest of the team best of luck over the next 2 years in finishing it out. It's such an important project for Ireland. It's absolutely critical that it's a success. So best of luck with it. And thank you very much for an excellent presentation.
Fantastic. Thank you, Joe.
Thank you, everyone.
Thank you, Susan. Cheers.